Let's start. Okay, so today will be, I guess, very much connected to the talk by Gerard yesterday. So I think Gerard didn't. So are you here, Gerard?
Not yet.
Not yet. Okay.
Copy.
So yeah, I think Gerard didn't give the definition of a cat K space, but what I will give today is the circle of ideas in the realm of smooth manifolds, which gave a theorem which has been taken afterwards in the realm of metric spaces as a definition of negative curvature. So this will be the Cartan-Alexandrov-Toponogov theorem, or yeah. So the attribution of this theorem is a little bit nebulous, but it's not a big problem. So maybe let's state the theorem that I will prove. There's a lot of variation, and I choose just the simplest case because it's a bit easier to prove, and we can give a more or less full proof without too many hassle, or without hiding too much under the rug. So the theorem is the following. So and basically the idea is to compare manifold with usually one-sided curvature bound with the model spaces of constant curvature. And Gerard introduced the model spaces yesterday. Took some time on the sphere and the hyperbolic space. We will just do like a comparison with Euclidean space, but all these theorems have counterparts when one work with non-zero curvature bound. So let M and G be a complete. Let's say simply connected to be really simply connected manifold with non-positive sectional curvature. So this is the setting. And maybe I will draw a picture, I guess, with Gerard's lecture from yesterday. This will be, or maybe I should stick to the notation from yesterday. So E2 is the Euclidean space, so I write DS2 for the usual flat metric. And so what that says is that if you take a geodesic triangle in MNG, so it's P, Q, R, you take a Euclidean triangle with the same side lengths. So let's say P bar, Q bar, R bar. Then you pick one point, let's say X, on the side, and one point X bar, which is in the same position. So yeah, maybe let's put markings on the side. So this would be the same length as this. This would be the same length as this. And this should be the same length. Okay. Then let's consider this distance and this distance. What the theorem says is that in that setting, the distance in E2, or in, let's go with the distance in G first. So here the distance on the left, so with respect to G between P and X will be smaller than the distance in E2 between P bar and X bar. And so we will see, so triangles in triangles in spaces with non-positive curvature tend to be thinner than Euclidean triangles, and this can be pushed to a very strong degree with the notion of delta hyperbolicity, at least at big scale. So that was what Gilles was talking about yesterday in the second lecture. But here, with just a zero curvature bound, we have this notion of smallness, of thinness of a triangle, which is not as extreme as delta hyperbolicity, but already has a lot of consequences. Okay, maybe let's do a little poll. No, not that one. So okay, so like yesterday, I will put sometimes just to have feedback from the audience. I will put some polls in the chat. So I've just put one. So and the question is like I've put some assumptions here. I've put completeless, which is in this. Which is in most cases is really necessary in this business, and I've also put simple connectedness assumption, and I can be lazy, so that might be out of laziness because this is easier to prove in that setting, or that might be because it's necessary. So I'm asking you whether this simple connectedness assumption can be removed. So people are voting. Thank you for your participation. Okay, so most of you, I guess, already knew the story or are very clever, because I could have, think when I first saw it, I didn't see the point of simple connectedness at first. But most of you didn't fall into the trap, so yes. So simple connectedness is important. Why is that? Because let's assume M is compact. This is not really important, but this will help a little bit. So if M is compact and pi1 is not 0, then there is a periodic, periodic geodesic, which is length minimizing. And what that gives us, when you have a periodic geodesic, let's call it gamma, you can take 3 points, for instance, evenly spaced inside it. And so the comparison triangle would be like this one. And the length here between, so that would be my point X here, like P, Q, R. And since we have a minimizing geodesic, the distance between P and X here is exactly half of the length of the periodic geodesic, which will be bigger than what we have here. So here we cannot have, so yeah, the theorem doesn't work without the simple connectedness assumption. But actually, especially in negative curvature, it will work at small scale, like before inside balls which are of size roughly the injectivity radius. Maybe you have to take a little margin. Maybe you have to go like inside the convexity radius, I guess. Yeah, I guess. If your triangle is contained inside a ball where you have uniqueness of geodesics, basically this is what the convexity radius is, then that will do. Okay. This theorem has a counterpart in non-negative curvature, which is a little more complicated to show, but which doesn't require this simple connectedness assumption. That's okay. So now so the goal of this lecture will be to set up the tools that allows to prove this result. There are a number of corollaries which are actually just more or less just plain Euclidean geometry. Once you have that, you can do like angle comparison, which I guess Gerard told us in between the sphere and the plane, or hyperbolic space and the plane. So from this, you can show that the angles of the triangle in M are smaller than the angles of the triangles in E2. And there are several other versions. We will encounter, and what we will prove actually is a more analytical fact on distance function, which is also useful, which is a useful way to think about it. Okay, so this will so the proof of this kind of results in the smooth realm is based on the analysis of distance functions. So okay, let's give a definition first. So MNG smooth manifold. So this is a really local statement. So we only need, for the definition of smooth function actually, so we only need to work inside some open set in M. No. And I take a real valued function, which I will assume to be smooth. So we say it is a distance function if it satisfies the following relation. The norm of the gradient squared, if you want, is constant equal to 1. So this is called, like in the PDE realm, the Kernel Equation, if I'm not mistaken. And this is actually the most sorry. This is actually what, when people want to compute distances on a surface in a practical way, like given by a mesh and stuff like that, or Riemannian metric in. So yeah, when people want to compute distance function on real stuff, to feed data or stuff like that, what they do is they try to solve this equation rather than trying to minimize this length of curves or stuff like that, or solve the geodesic equation. They solve this equation instead, which gives you the distance from a point to all nearby points in one batch, for instance. Yes, Diane, that's it. Okay. So maybe a lemma, when we will see why it's in some sense like understanding this kind of equation is in some sense understanding geodesics. So the lemma, so I will set dr. Okay. Yeah, no. Before the lemma, I will do something else. So with every distance function comes a very convenient coordinate system, which are called Fermi Coordinates, at least locally. And so how do you see that? How are they defined? So let's say R naught in R, called sigma R naught to be the preimage of R naught by this distance function. So let me draw a picture. So this would be a. So I've assumed the function to be smooth. It has non-vanishing gradient. So this will be some hypersurface. And at least locally, like with the inverse function theorem, you have like a foliation by. So that will be like, let's say, sigma R naught minus epsilon. And here would be sigma R naught plus epsilon. So you have this foliation of the at the neighborhood of any point of by level sets of the distance function. And so gradient R, maybe I could zoom a little more. No, I can't. Okay. Gradient R here is just the normal field and unit because of the condition on R. So it's just the unit normal to those hypersurfaces here. And so we can define the coordinates in the following way. So you start with a point in this hypersurface times some real number, let's say, in some interval around 0. You go to M, and so let's call that point X, and then you follow the geodesic in the normal direction for time epsilon. So xt is mapped to the exponential at x, Riemannian exponential, and just follow the geodesics, t times gradient R at x. So, and this gives good coordinates which are adapted to this thing, to this distance function. Okay. So now let's see what's going on with this. What's the relation between geodesics and distance function? So the lemma is the following. So I will often thinking of this setting, like we have a product metric more or less. Well, not quite. We'll talk a little bit about it afterwards. But we have this coordinate chart. So and I will often write del R for this R vector field, so for gradient R, and it kind of give a little more compact notation. Oh, sorry for that. And the lemma is the following, which says in particular that integral curves, so solution to x prime is equal to dr at x. The integral curves are geodesics. Integral curves of del R are geodesics. Okay. So how do you prove that? So this is pretty easy. So first, very easy observation is the following. So this is 1/2 of del R of norm of R squared, but this is 0 since this is 1. So we already have that the covariant derivative is normal to dr. And so we need to see what's going on in the other direction, in the direction of my hypersurfaces sigma. And so we will take vector fields of the form x of xt equal x bar of x 0. So where this is some vector field, any vector field on sigma r naught. And so this doesn't depend on t, on this t coordinate. So the Lie bracket of x and my radial vector field will be 0. So x del R will be equal to 0, which will be very convenient because this will allow us to compute the following stuff. So 0 is equal to the derivative. So just the same thing, like gradient R as 0 is a constant function. But then this will be twice nabla x del R del R. But then, yeah. So then you can exchange x and dr here because the vector field commutes. And then since this is constant, you can, since x is orthogonal to del R, you can exchange at the cost of a sign change, which is which is 3 here, which is not important here, you can put the del R here. Basically what you just say that del R of x del R is 0. Thus, so it's normal to the, so nabla dr is normal to the normal direction here. And it's also normal to the radial direction. And it's also normal to sigma, so it's 0. Okay, so we've seen how distance function help us understand geodesics. Now let's see how distance function relate to curvature. So this will be what we will try to understand. So yeah, maybe let me redraw my Fermi coordinate patch. So I have my foliation by sigma here. So I have my del R vector field, and so integral curves of the vector field here, normal to those hypersurfaces, so on. And they are geodesics. Yep. Okay, and since dr is orthogonal to sigma, we can write G, the metric can be written as dr squared plus some metric on sigma r, which I will call G sub sigma r. And this is just the induced metric on sigma r. So our full metric G is determined by this like generalized warp product metric, more or less. So yeah, this is a generalization of the warp product. So if r was the distance to a point, it would just be the polar coordinate in an exponential chart. But yeah, sorry? Okay, no problem. Okay, so now let's try to link that to more to other things which are built from the distance function. So we know that nabla r is the normal to the hypersurfaces sigma r. And what is the Hessian of r? So this will be so maybe let's write it on some vector fields. So this will be, by definition, more or less, nabla x, nabla r, inner product with x. So this is actually so since this is the unit normal, this is actually the second fundamental form of sigma r. Okay, so we still don't have any curvature. Okay. Now we will, and just a quick note which can be useful. The Hessian of R And actually, you can do that with any function, and this will come in handy. We will only use it for the distance function, but this is half the Lie derivative of g in the radial direction, and since in those Fermi coordinates the metric is written in that very simple form, so this is half the Lie derivative of the induced metric on this sigma hypersurface. In particular, if the Hessian is 0, we will see that in the next lecture. When the Hessian is 0, that means that G sigma doesn't move with R. G sigma R is independent on R. So that means that we have a product, and this is one way to prove the splitting theorem for non-negative Ricci curvature. Okay. And so now, where does curvature enter in all of that? One way to see where it comes from is the following. So Peterson called that the fundamental equation of Riemannian geometry. Well, I guess a case could be made for other equation, but this is a very useful one. Romanian. So that, yeah. So that's what Peter Peterson calls it in the book, and this is the following. So Hessian is a quadratic form. You can try to look at the Lie derivative of the Hessian. So let's see. So what we're interested in is how does the second fundamental form moves along those sigma r hypersurfaces, and it moves in the following way. So yeah, maybe one quick note on the Riemannian curvature tensor, because there is a big mess of convention here. Okay, so let's so think of the Hessian as so the Hessian is a quadratic form, but since we have an inner product at end, we can see that as an endomorphism of the tangent bundle, which is called the shape operator. And so the Hessian here is just the square of this endomorphism. So there's a lot of way to see that, and we'll see that afterwards. Okay. So where am I? Okay. So there are other versions. You could prefer using the covariant derivative instead. Oh, I think my tablet share has frozen. So I guess I will restart the screen share. Okay. Okay, this seems to be all right. Has the display been updated for you? Okay. So yeah, maybe let's talk a little bit And so we will quickly prove that. But first, let's talk a little bit about what's involved. What is my definition of the 4-0 Riemann curvature tensor? Since, as I said, there are a lot of different conventions floating around. So this might be minus what you're familiar with. So I apologize with that. Yeah. So nabla x, yeah. Nabla x, nabla y, z minus nabla xy z. Then I put z, yeah, sorry, inner product with t. So yeah, what's important is that this is some sectional curvature. So if you plug a vector field x inside it, so this is the sectional curvature of x times r. So sorry. So sectional curvature of x times r times g of xx if x is not of norm 1. So here we see that the sectional curvature via this kind of matrix equation, it's a matrix Ricci equation, controls the evolution of the extrinsic geometry of sigma. So the inner curvature, intrinsic curvature of M, controls the evolution of the extrinsic geometry, extrinsic curvature of these distance hypersurfaces. Okay. Yeah, maybe a few. So the proof is just a computation, but if you've never seen it, maybe it's a good idea to do that. Okay, yeah. So I take x to be any vector field, and so you want to differentiate this, the direction of x. And so what is that? Well, you use like a Leibniz rule. And so there are two extra terms, one for each x. But since the Hessian is symmetric, I can write it like that. So if you're more accustomed to covariant derivative of tensor, so covariant derivative of tensor extends covariant derivative of vector field to tensor, and like Lie derivative of tensor extends the Lie bracket of vector fields to tensors. So that's why here the Lie derivative of vector fields of one vector field with respect to the other is just the Lie bracket, and you can extend it to tensors as you do for the covariant derivative. It's not tensorial in the direction in which you're differentiating, so you have to be a little extra careful. But in some sense, and here in that case, it's a natural thing to look at when you look at evolutions in that sense. Okay, so this is the derivative of nabla x dr. Yeah, I don't think I'll do the full computation. I'll just show where the curvature appears here, and then you can finish afterwards. To Hessian of r, sorry. Hessian r of drx x. And so like you use once again Leibniz rule. oh, sorry. The Hessian of R in XX is nabla R, nabla X dr, comma X. Is it what I was saying, Erwan? Your remark? Are you okay with what's written right now? Okay, perfect. So, okay, and -2 blah blah blah. Let's not forget that, but I'm not touching that. And this is where the sectional curvature will appear. Okay. So how does it appear? Yeah, well, basically you use the definition, and we will use also minus r drx drx, and then you need to be very careful with the signs. So I'm taking a look at my notes. Del R x. Okay. Then so that comes with a plus sign. So yeah, maybe people prove that do the computation in some other way. There's with other notations. There's a lot of ways to do this kind of computation. Maybe as many as there are different geometers, but I guess it's good to be exposed to a lot of those techniques and conventions and stuff like that to just find the one which is good for you and with which you are proficient and don't make too many errors. Okay, so now we are more or less good, so you have to look at that. So why did I go this far? So this is 0. We have seen that together. And actually, so this is Hessian of dr comma x. So this one takes one less Hessian here, cancels with one of the Hessian here. And then basically you write this last term here. This one. You write this last term as a Hessian, and with that, it will give you a Hessian squared. Using. Oui, on peut aussi faire que. Yeah, we can do that. That's yeah, I guess most of you who have used Zoom will know that. So Erwan Aubry sent me a private chat message, and it's hard to make a difference between the two. But yeah, I agree. But sometimes, yeah, in particular, yeah, if you look at x, if you take x to be one of this vector which is independent on R in those Fermi coordinates, then all those Lie bracket would cancel, and yeah, that would be much faster. I agree. Yeah, and we could just exchange here to get the Hessian squared. Yeah. So as I said, there's lot of ways to do these computations, and what you need is to find something which is good for you. Okay, so now let's do a corollary. Yeah, so now we are going to the setting that we wanted to do. So Mn is with, so I will write K for the sectional curvature. Maybe so if you read the note afterwards, I guess it's better to be explicit here. And simply connected. And this is an analytic, and we will prove an analytic version of the distance comparison, the triangle comparison theorem that we stated at the beginning, and we will see afterwards why it's an analytic version of that. So now we will specialize our computation here to distance function with distance to a point, which is a distance function. So P in M, and R is the distance to P. Okay. Okay. Then I will state two things. So the Hessian of R is bigger than 1 over R GR. And this is true on M minus the point P, because distance is not smooth at P. But you can do it a little better by using what Peterson calls modified distance function. Basically, you want things which are smooth in the model space, as smooth as possible, and built from the distance in the model space. That makes a very good quality of life improvement in those business. So in the Euclidean space, if you want to build a smooth function, you just square it, and you might as well square half of it to get a Hessian which is just one, just the identity. And this will be true on all of M. So this will work only, so yeah, maybe let's make a remark. So in particular here, I'm the distance to a point is smooth on M minus the point, because M is simply connected. So this is the Cartan-Hadamard theorem. Because, yeah, and the curvature is negative. Because M is simply connected and K is negative, okay? Yeah, and this is the Cartan-Demar theorem, which is maybe the most clear proof of that. It's going through the variational theory of geodesics and Jacobi fields and such, and I didn't want to tell this part of the story in these lectures. So, and this is more standard than this comparison estimate. So I'll assume that you're all right with that. But maybe some the proof will actually be very local. Proof is local. And so this will actually works whenever the distance function is smooth. And so the result is okay. Wherever, yeah, maybe not state it like that, is okay on m minus the cut locus of p, and p if you're using R and not the modified part. Okay. Okay, so let's see how this goes. Okay, so we know that R is smooth. Okay, so first let's notice that when R is very small, you can see that in Euclidean coordinates, normal coordinates, the metric and the distance look as in the Euclidean space. So the Hessian of the distance function will look at just as what it is in the Euclidean space. So what that tells us is that, and also the distance spheres will just look as Euclidean spheres. So the Hessian of the distance is equivalent as R go to 0. And here we are using that we are looking at the distance from a point. 1 over R G sigma R. Okay? So just as in the model space. And so this is something which is a little more complicated in metric spaces, because you don't have the fact that at very small scales, things are flat. Okay, so now we want to show this inequality here first. We will see the second one afterwards. We want to show this. So we will take a derivative and see. So we know that it goes to 0 when R goes to 0. So we'll take the derivative and see what's going on. There should be something. So what is the derivative then of Hessian of R minus 1 over R G sigma R? Then we can use our computation. So this is minus R of, so this sectional curvature term. Okay. Then plus the square of the Hessian seen as a matrix. And then we differentiate that guy. So we have plus 1 over R squared G sigma R. So as a matrix, this is the identity. So this we could as well put a square here, even if it's bad practice, I'd guess, to mix like quadratic forms and matrices that far. And then so that's what we said before. The Lie derivative of this metric on the hypersurfaces is just the Hessian of the distance function with factor of 2. So we are in luck because this is negative, so that is positive, and so this is greater than Hessian r squared plus 1 over r squared g sigma r. Forgot the square here. No, there's no square here. Minus 2 over r Hessian r, and here a kind of miracle appears. Is that you can see that as so this is just Hessian r minus 1 over r g sigma r squared. And so as matrices, these are non-negative as quadratic forms. So when you plug in a vector like a constant vector, that will tell you that the Hessian r xx minus 1 over r norm of x squared is an increasing function of r. So it's 0 when r equals to 0, and it's increasing, so it's non-negative. So the Hessian of r is greater than 1 over r g sigma r. Okay, so what time is it? It's almost 10. Okay. Now, so we have the first part, then the second part is just an easy computation. So what is the Hessian of half So you can see that as the covariant derivative of the exterior, like the one form, which is the exterior derivative of r squared. So that's the covariant derivative of r dr, this one form. And so now you differentiate the product. So covariant derivative of the r function is dr. So we get tensor, we get dr squared, and then we get Hessian r. R times Hessian r, sorry. And since Hessian r is bigger than here, we plug that. And so this is bigger than dr squared plus g sigma r, which is exactly g. Okay. So this gives us the fact that the Hessian, was a bit sloppy here. So this is a comparison between quadratic forms. So I guess I should have written like that. Okay. So this is called the Hessian comparison theorem. We will see tomorrow that there is also a Laplacian comparison theorem, but in non-negative Ricci curvature. And we will do a completely different kind of proof of that. Completely, no, but we will start with something else. Okay. So maybe some remarks. this trick here, recognizing a square, doesn't really work when like you want to study like non-negative curvature. Yeah, because you have a square, it's greater, it will be less than a square, but that doesn't tell you anything. So non-zero upper, and also yeah, actually, when you have a constant here, you can probably say something. But yeah, let's just say that non-zero upper bounds and lower bounds, in all lower bounds, require a better understanding of this Ricci equation of this matrix Ricci equation. You can see that from this equation you can control the lower and the higher eigenvalues of A, and then this gives you another version of the comparison theorem. And another remark is that so when dealing with non-zero bound, so yeah, it's still maybe a good idea to work with 1 over r squared than with r, but you can do even better. Instead of half of r squared, to have like a very, very workable Hessian estimate, you use yeah, those two cases. 1 minus cosine of r. Let's say if the if comparing to the sphere, let's say, and hyperbolic cosine of r minus 1 if comparing to the hyperbolic space. So, and this will give you basically the... So what are these? In the model space, these functions have constant Hessian equal to the metric, if I'm not mistaken. Just as half of r squared in a Euclidean space. And so you will get the comparison here. Maybe some extra remark for lower curvature bounds. So the proof is more complicated, but the bounds, the Hessian bound so yeah, let's say with k equal to 0, so the Hessian bound will be that it's less than g. So n is global in a weak sense, and that doesn't work. So you can interpret this Hessian bound as some convexity along the geodesic, some convexity estimate along the geodesic, and so yeah, which we will see when we will try to go back to triangles. And this is in one of the strengths of a non-negative curvature is that this holds in a weak sense, whereas this doesn't on a like non-simply connected manifold with negative curvature. Okay, so now let's go back to triangles. And let's see what this Hessian has to do with triangles. And it's not complicated. So yeah, maybe let's or maybe use technology. Okay, no, let's restate the theorem. So maybe Cartan, Alexandrov, Toponogov. Although there seemed to have been like, what was his name? Oh, I don't have it. Maybe? No. There was at the beginning of the 20th century, there was an Italian mathematician which had more or less figured it out, but in a strange language. I'll try to dig up the reference. But people didn't do anything with it, so people forgot about it, basically. So, and I guess it was only for surfaces. So let's go back to triangles. So MNG and simply connected. And E2 with the Euclidean metric. And then we will do the following. So yeah. My comparison triangle. P, Q, R, my first triangle. Then my comparison triangle. P bar, Q bar, R bar. Point X here, X bar here. And yeah, so these are comparison triangles. The median here, or yeah, not quite, but so, and what we will prove is that the distance with respect to G between P and X is less than the distance in E2 between P bar and X bar. And this is actually not too complicated. So how do we prove that? Now that we have the Hessian comparison theorem. So let R be the distance function from P. Okay. And maybe let's parameterize that by here. So gamma of T. So this is and here would be like gamma bar of T. Parameterize my lower size of those triangle. Set set big L to be the distance from Q to R. Yeah, maybe something that will show up in the... I don't know if Gerard or Gilles use these notations yet, but I do sometimes, and it's very convenient. So in a metric space, to lighten the notation, you can sometimes use this absolute value. And so that helps. Like Burago, Ivanov in their book use that a lot. Yes, Erwan, Pizzetti, thank you. So Pizzetti is the guy who found that in case of surfaces, I think. But like in 1907 and 1917, but people didn't quite notice until like the 30s with Élie Cartan and later, and it really came to fruition and came to have a lasting impact with Alexandrov and Toponogov afterwards. Okay. Thank you, Erwan. So L is the distance from Q to R, and so I will consider a function f, which will map t between 0 and L to the distance from P 1/2 distance from P to gamma of t squared. So this P equal to 1/2 R composed with gamma squared of t. And I will do the same in the Euclidean space. So f bar will be, I map t from 0 to L to really the Euclidean norm, like P bar minus gamma bar of t squared. So what can we say about these functions? So these are smooth functions of the t variable, and they satisfy the following. So since gamma is geodesic, unit speed actually, if you want to compute the Hessian of any function u in the distance in the direction of any tangent vector to the geodesic, sorry. Maybe I should have taken a break. Okay, but we're almost done anyway. So the Hessian of u is just dt squared of u composed with gamma. So this can be taken as a geometric definition of the Hessian. And so we have that f second of t so will be equal to Hessian of half of r squared of gamma dot, and with our Hessian comparison theorem, so we will know that this will be greater than 1. Now f bar of t, if I differentiate it twice, well, you're differentiating an inner product like that, you will see that it's constant equal to 1. Thus, if I take f minus f bar and I differentiate it, I get something which is bigger than 0, and f minus f bar is convex. Moreover, f of 0 is equal to the distance. So f is the distance here, so it's equal to the distance pq in M, which by definition of a comparison triangle is equal to the distance pq bar, which is f bar of 0. And the same goes at L. F of L is equal to f bar of L. So we have a convex function which so yeah, f minus f bar is convex and vanishes at 0 and L. And for t, any t in 0 and L, so f minus f bar is negative. So we have that, and what does it tell us? So half of distance from P to gamma of T squared is less than half distance from P bar to gamma bar of T. And when T is the value of the parameter corresponding to the point X, we get with X equal gamma of some T, and taking the square root and multiplying by 2, we get Px less than P bar X bar. Okay, so that concludes the proof of the triangle comparison theorem in negative curvature. And as you see, like as soon as we can make sense of this computation, this is okay. So this will work as long as my geodesic here stays where the distance function, oh, I have a conflict of r's here. Well, but when the distance to P is convex, is not convex, is smooth, so that will work basically before as soon as PQ and PR as distances are smaller than the convexity radius at P. So we can see that we can make it work locally. Okay, so you can look, for instance, at the book of Peterson's for some application of this idea. I didn't prepare, but this you can use that to prove things about like fixed points of isometries in negative curvature, and in turn to give stuff like the Priceman theorem, which says that the fundamental group in negative curvature is always torsion free, which is a very nice result. Okay, so we're 10 minutes in advance. Like, if you have questions, I guess that's a good time for it. Cija is here. I didn't overlap too much with what you're gonna say on cat spaces.
No, that's fine. Perfect. And
okay.
And the lecture on cat spaces will be given by Philippe, in fact.
Okay. Hi, Philippe.
We just arrived here. But I like the point of view that you choose here.
Thank you.
Are there any questions in this room? Okay.
I'm gonna get some water. See if you have questions afterwards. I'm coming back in a minute.
Quoi? Non, mais c'est une basse et à côté, c'est une contrebasse. Donc, c'est un bassiste. Et il pourrait nous jouer un morceau de basse.
Thank you, Erwan.
Some people are asking for who playing your bass. Voilà la réponse. Okay, on our side, we don't have any questions.
Okay. People online, were things clear? Tomorrow we will do comparison geometry for non-negative Ricci curvature. So the methods are not quite the same. It's more maybe a little more analytical, but like this analysis of distance function will still be a big tool.